Welcome to Shri Learning Academy. Let's simplify Peterson's algorithm. Imagine two processes trying to enter the same critical section at exactly the same time. Both believe they should go first. Neither wants to wait. If the operating system does not controls properly, shared data can be corrupted in a fraction of a second. A bank balance may update incorrectly, a file may be overwritten, or a printer queue may become inconsistent. This is where synchronization becomes essential. But before modern hardware, instructions, and advanced locking tools became common, computer scientists first explored whether software logic alone could solve this problem. One of the most famous results of that effort is Peterson's algorithm. To understand why this algorithm matters, remember that in earlier topics we discussed the critical section problem. A critical section is the part of a program where shared resources are accessed. If two processes enter that section together, race conditions can occur. We also learned that a proper solution must satisfy three important conditions. First is mutual exclusion, meaning only one process enters at a time. Second is progress, meaning if no one is inside, some waiting process should be allowed in without unnecessary delay. Third is bounded waiting, meaning no process should wait forever while others repeatedly enter. Peterson's algorithm became famous because it satisfies these conditions for two processes using only shared variables and careful logic. Let us imagine two processes named P0 and P1. Both want to update a shared counter. Without synchronization, both may read the same old value and then write conflicting results. Peterson's idea uses two shared elements. The first is an array called flag, where each process announces its intention to enter the critical section. If P0 wants to enter, it sets flag 0 to true. If P1 wants to enter, it sets flag 1 to true. The second shared variable is called turn. This variable indicates whose turn it is to enter when both want access at the same time. These two simple ideas, intention and priority, are enough to coordinate access. Now let us see how process P0 behaves. When P0 wants to enter the critical section, it first sets flag 0 to true, which is like raising a hand and saying, I want in. Then it sets turn to 1, meaning it politely gives priority to P1 if there is a conflict. After that, P0 checks a loop condition. It waits while flag 1 is true and turn equals 1. In plain language, P0 waits only if P1 also wants to enter and it is currently P1's turn. If either P1 is not interested or the turn has changed, P0 proceeds into the critical section. Once done, it sets flag 0 to false and exits. Process P1 follows the same mirror logic. It sets flag 1 to true, then sets turn to 0, offering priority to P0 during a clash. Then it waits while flag 0 is true and turn equals 0. If P0 is not interested, P1 enters immediately. If both want access together, the turn variable decides who waits and who enters first. This symmetry makes the algorithm elegant. Both processes are treated fairly, and neither needs a central controller. Let us use a real example. Imagine two students sharing one printer in a lab. Student A and student B both click print at nearly the same moment. Each places a sticky note saying, I need the printer, which represents the flag variable. Then each politely says, let the other go first if needed, which represents setting the turn variable. Since both cannot print at once, the final turn value decides who gets access first. One prints while the other waits. After finishing, the first removes the sticky note and the second proceeds. No paper jam, no mixed pages, no confusion. What makes Peterson's algorithm powerful is that it satisfies mutual exclusion. If P0 is inside the critical section, P1 cannot enter because the waiting condition will block it. The same is true in reverse. It also satisfies progress. If only one process wants access, it enters without delay because the other process flag is false. It also satisfies bounded waiting because a process cannot be postponed forever. Once one process finishes and lowers its flag, the waiting process gets its chance. These guarantees made the algorithm a landmark in synchronization theory. There is another important concept here called busy waiting. While a process is waiting in Peterson's algorithm, It repeatedly checks the condition in a loop. It does not sleep or block itself. It keeps using CPU cycles while waiting. Earlier, we discussed busy waiting versus blocking, and this algorithm is a classic example of busy waiting. For very short waits, this may be acceptable. But if the wait becomes longer, CPU time is wasted. That is one reason modern operating systems often prefer semaphores, mutexes, or blocking locks instead of pure spin loops for many situations. Although Peterson's algorithm is brilliant, it has limitations. First, it is designed for only two processes. Extending it to many processes becomes more complex. Second, it assumes that memory operations happen in a predictable order. Modern processors may reorder instructions for performance, and modern compilers may optimize code in ways that break naive implementations unless memory barriers are used. Third, real operating systems need scalable solutions that work across many threads and CPU cores. So while Peterson's algorithm is historically important, it is rarely used directly in production systems today. Still, its educational value is enormous. It teaches that synchronization is not magic. It can emerge from clear reasoning, shared state, and disciplined rules. Before hardware atomic instructions like test and set or compare and swap became common, algorithms like this showed that software itself could enforce order. That idea influenced many later synchronization tools we use today. When we move into hardware solutions, semaphores, mutexes, and monitors, you will notice the same goals repeating again and again, only one at a time, no unfair delay, and no endless waiting. Peterson's algorithm simply expresses those goals in one of the purest forms ever created. So, whenever you hear that two threads are competing for shared data, think of two polite but determined people at a narrow doorway. Each wants to enter, neither wants chaos, and some rule must decide the order. Peterson's algorithm is that rule. Simple variables, simple logic, and a deep lesson in how operating systems maintain order in a world full of simultaneous activity. That is it for this video. See you next one.